Hello, YouTube. We're back. Okay, let's do it. You ready for number 6? All right. Listen up. Here's our final review for Chapter 7, Chip Logic. Includes a little bit of everything in the other chapters, Boolean logic and all that stuff. All right, here we go. You are the Macintosh Classic. Okay. Steve Jobs feeds you a floppy disk. I'm putting the numbers A is 2.7x, and B is D.9x, right? All right, so you got the numbers A and B, the variables A and B. All right, so number 6, display your input to the console. In other words, convert this to base 10. How did you do that? What did you get? You did this already. Well, it's still 2 point, right? Okay. Now, how did you get this 0.7 from hex to base 10? Well, there's 2 ways I can think of what you do. You said 7 divided by 16 on the calculator. Did you do it on the calculator? What did you get? 4,375, right? Because the 2 is in the 1's place, but the 7 is in the 16th place, right? Okay. So you can do 7 divided by 16 on the calculator, or realize that a 16th in base 10 is simply 0.0625, and you can multiply that by 7 and get the same thing. What's D mean? 13. So there you go. Just write 13 in base 10. That's not tough. Now what do you do with the 9? Divided by 16 or multiplied by 0.0625, and what did you get? 5625. Perfect. That's question 6. Question 7. Convert these hex numbers to binary. Well, how do you convert a hex digit to a binary number? You have 4 bits, right? So 1, 2, 3, 4. 1, 2, 3, 4. How do you write 2 in 4 bits? 0, 0, 1, 0. How do you write 7 in 4 bits? 0, 1, 1, 1. All right, let's do it over here. How do you write 13 in 4 bits? 1, 1, 0, 1. How do you write 9 in 4 bits? 1, 0, 0, 1. All right, that's questions 6 and 7. This is terrible. Your test tomorrow will be very similar. Okay, you ready for 8? All right, let's add it to chip level. Here we go. Okay, so what's A plus B? It's 1101.1001. Well, that's B really. Plus 10.0111. That's A really. But we're adding it, doesn't matter. So go ahead. 1 and 1. 10 carry 1, 1 and 1. 10 carry 1, 1 and 1. 10 carry 1, 1 and 1. 10 carry 1. Line up the decimals. 1 and 1. 10 carry 1, 1 and 1. 10 carry 1. This is boring. 1 and 1. 10 carry 1, 1 and 1. 10. Amazing. Did you get that? Yes. It's so familiar. This is the exact same question in the last step. All right. 1101.1001 minus 10.0111. All right, let's subtract. 1 minus 1, 0. 0. 0 minus 1. You can't do that. You can't borrow from here, so bring it from there. So 0 then, 10 but 1 then, and 10 minus 1 is 1. And 1 minus 1 is 0 minus 0 is, and 1 minus 0 is 1. Don't forget the decimal part, right? Now 1 from 0? You can't do it. You gotta steal. Okay, so this becomes 0, this becomes 10. 10 minus 1 is 1, and 0 minus nothing, and 1 minus nothing. And then, is anyone disagreed? You okay with this? Yes, everyone got that? Did you get this on your own? Okay. Everyone okay with this? Questions how this works? Problems, comments? Right now would be a good time. Okay? All right, now, convert this back to base 10. Well, how do you convert a binary to base 10? Look at the placeholders, right? 1's place, 2's, 4's, 8's, 16. So there you go, 16 to base 10. All right, so how about this one? A 1, a 2, no 4's, and an 8. 11 point what? 125. Why? How do you know?
Because that's 1/8.
A half, a quarter, and 8th place. Right, you have 1/8.
That's what I like to see. Oh, yeah.
All right, so that's in binary. That's in decimal. That's in binary. That's in decimal. All right, anyone disagree with any of this so far? Questions 6, 7, and 8? All righty. 6, 7, 8, 9, actually. All right, 10. Well, base, listen,
Clifford, turn around.
the 16 in base 10, Clifford, you have your own desk, huh? All right, 16 in base 10 is 1 in base 16. 10. 10. That's what hex means. 10 in base 16 is 16 in base 10. All right, but how do you convert this? Well, 11 in decimal is a digit in hex. What is it?
Oh, damn it. Oh.
It's B, right?
Yeah.
Right? You can convert these 4 bits right here to 1 digit if you want. All right, how about this one? These 4 bits equals how much in binary?
8
2.
16.
So you're done.
Oh. 1 8 is not equal. Oh, wait.
It's 16, yeah.
Oh.
All right, so that's page 1. Are you good on page 1? Okay, you better put it down because the last time we're doing this. Yeah.
But this is the last one.
Well, just like over here, we converted one hex digit to 4 binary digits, right? We're doing the exact reverse over here. 4 binary digits is 1 hex digit. Go back. So this means 2 in 4 bits, right? So just write 2. This means 13. So, I'm sorry, 11. So write B. It's a digit number 11. Right? All right. So that's page 1. You ready for page 2?
Yeah.
Alrighty. You are the 4-bit computer. Convert the following calculations from unsigned binary whole numbers to 4-bit computer signed numbers. Complete the indicated operations with 4-bit computer signed numbers and output your final answers as they would appear on the console. In other words, signed base 10 numbers. Okay, good. So, 11 says what's 0101 plus 0011. Just do it like a computer.
1,000.
1 and 1.
10.
10 go to 1, 1, 1. 10 go to 1, 1, 1. 10 go to 1, 1, nothing.
Uno.
So what's the output?
-8.
Not really.
Error!
That would be a negative result, but we're writing 2 non-negatives. That doesn't make sense. So error. Overflow error. The numbers are too big. Because you're adding 5 and 3, you should get positive 8. You're going to get to that. The 4-bit computer has a range from -8 to +7 integers. That's all.
That's horrible.
That's terrible. You got to start somewhere. We had 4-bit chips when we started. 4-bit computers, we did. All right. This is number 12. What is 0111 plus 0111? Be the computer. The computer doesn't know if there's an error yet. Just do the work. So 1 and 1. 10 carry 1. 1, 1 and 1. 11 carry 1. 1, 1 and 1. 11 carry 1. 1 and nothing. So what happened? Error again. Same reason. It can handle that input, but it can't handle that output. All right, so that's 11 and 12. We're at 13. Questions, comments, problems? All right, 13. 13 says 0001 minus 0110. This computer doesn't know how to subtract. So what do you do instead? Add the opposite. So I'm going to take a +6 and change it to a -6. How do you do that? Flip it. 1001 and add 1 to that, so 1010. So I'm going to take a +1 and add to it a -6 instead. Okay. But you know the answer. What's 1 minus 6 normally? It better be -5 when you're done. All right, so let's add 1 and nothing. 1, nothing and 1. 1, nothing and nothing. 0, 0 and 1. So you got a 1 here that's an error, right? No, because these are mixed. We're adding a non-negative to a negative. You can't get a negative, that's okay. Is that -5 like you expected?
No.
It is, because if you convert that back, you get a +5. Let's see. 0, 1, 0, 0, plus 1, 0, 1, 0, 1. Yeah, that's a +5. So that's -5 because that's +5. So the answer is -5 base 10. Zeros become 1s and 1s become 0s. That's it. Then you still add 1 also. So that does the changing of the sign. As that changes a +6 to a -6, that changes a -5 to a +5. All right, so this is the work here. This is the answer here. That's all you have to show me. All you have to show me is this and this. That's all I need to see. You can do scratch work on the side if you have to, but I need to see this, I need to see this. Okay? All righty. Ready for 14? Should I move ahead? Yeah. All right, here's 14. 14 says, what's 0011 minus 1101? Again, I don't know how to subtract. I'm the 4-bit computer. So what do? Right, so take this negative number and convert it to what? Well, 0, 0, 1, 0 plus 1, 0, 0, 1, 1. What is this? What is this number in the computer? Positive 3, so that had to have been negative 3. So we take a positive 3 and subtract the negative 3. What should you get in base 10?
8.
A positive 3 minus a negative 3?
Oh,
6, right? So let's say that we do. We're going to take the positive 3 plus the other positive 3. If we go to the heck at positive 6, this should be obvious. 1 and 1, 10 by the 1, 1 and 1, 1 and 1. 11 by the 1, 1 nothing, 1 nothing, nothing. So you got a positive, or at least a non-negative, 6, isn't it? So that's your output screen. I need to see this work. I need to see this answer.
Why don't you convert that one back because you're allowed to?
Well, you don't have to because it's non-negative. I know what it is. These are easy to read. When there's a 0 in front, it's like a positive normal 6. Right? So you don't have to convert that one back. I converted this one back just to see what the heck it was. I wasn't sure what that was. I converted it to positive 5, so I knew that meant negative 5. Just so I know what to put the opposite. But here, this goes straight to here, right? You can do positive 6 in your head. All right, and 15, you ready?
Yeah.
All righty. So again, we're subtracting 0, 1, 1, 1 minus 0, 0, 1, 1. Technically, you could cheat here because this number is bigger than this number, so you can just subtract normally. But that's not what the computer does. Show you what the computer does. Take the 0, 0, 1, 1 and do what? Add the opposite. So flip it and you get 1, 1, 0, 0, and add 1 to that, you get 1, 1, 0, 1. So if that's positive 3, that's negative 3. So I'm going to take a positive 7 and add to it a negative 3. And I better get a positive 4, right? Because 7 minus 3 should be 4, right? You can actually do it here. Cancel, cancel, 1. This actually works. But do it like a computer, that's the point. So 1 and 1.
10.
10 go to the 1. 1 and 1. 10 go to the 1. 1, 1 and 1. 11 go to the 1. 1 and 1. 10 go to the 1. What happens to the fifth bit? It's ignored. There's no hardware to carry it. So it's really only a positive. What? That is positive 4, isn't it? And that's what you would expect. A positive 7 minus a positive 3 should be a positive 4, or you're left doing something right. All right, did you do the truth table yet?
No.
All right, so about it. I need a truth table for x nor y, x nan y nor with z. All right, so how do you make a truth table out of this? How many columns do you need? How many variables to start?
3.
3. All right, so x, y, z. All right, let's line this up a little bit.
What was the answer to the last question?
That's all there is. We can't do this, we do this instead because that's negative 5 right there. We're adding negative 5 instead of subtracting. Sorry, negative 3 instead of subtracting. All right, going back. All right, so let's see, 1, 2, 3. How many rows do I need? You know, there must be a better way to do this. Hang on. Let's do this. 1, 2, 3, 4, 5, 6, 7. How many columns did you get? Did you finish this? I think I have 7, right?
Yes.
So I'm gonna do 7 columns by 9 rows. There you go. That should do it. Is it 7 by 9 really? Because you need the head. All right, so I'm going to say this is x, y, z. All right, what was your next heading? X, y. What's your next heading? X nan y. What's your next heading? X nan y ORed with a z, then X nan y NORed with a z. Right? Okay. Is that okay? Are the headings obvious now? Are we good? That's called decomposition, logical decomposition. All right, so you just count 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. All right, how do you do that and? Multiplying the first 2 columns, so 0, 0, 0, 0, 0, 0, 1, 1. Okay. All right, how do you negate that column? You flip, that's the flipping the bit stuff, right? So what are you writing? 1, 1, 1, 1, 1, 1, 0, 0. All right, and now how do you do an OR? It's like adding, except when it's not. So we're adding this column, the last column we did with the Z column. So let's add 1, well, sort of 1, 1, sort of 1, 1, and sort of 1. Oh, 0, that's the only 0, right? Okay. So 1, 1, 1, 1, 1, 1, 0, 1. All right, and then you're negating that column, so you write 0, 0, 0, 0, 0, 0, 0, 1, 0. All right, that's third base. No, that's it. All you got to do. All you got to do.
Wait, what do you do? Oh, you do X and Y too?
Well, this was the question right here. How do you get that? That was the question.
Well, you need the X and
You
Y.
need the X, Y before you can not it. You need the X, not Y, or Z before you can not it. Right? All right, so I think there's 3 input columns and 4 output columns. And it's 8 rows by 7 columns. Okay, so now that you've decomposed this logically, it's easy to write the circuit diagram, isn't it? Right, because you need how many gates? There's it right here. There's 3 inputs, but 4 gates. Okay. So you're going to need a gate for the X, Y. You're going to need a gate for the X, Y not is. You're going to need a gate for this OR, and you're going to need a gate for this not. That's basically all there is. Remember, you don't need to use XOR, XNOR. You don't need to use NAND or NOR. You just need to use ANDs, ORs, and NOTs. That's all. That's all you're going to do. All right, so can we do the circuit? Everyone ready to go do the circuit? Yeah, but don't do that. I'm asking you to use only ANDs, ORs, and NOTs. ANDs, ORs, and NOTs. That's it. Keep it simple. All right, so here we go. We have 3 inputs, right? X, Y, and Z. So what was your first output column? X and Y. So how do you draw an AND? It's capital D, basically. And we're ANDing who? So just put it right here. Ding. So input X, input Y, output X and Y, right? Okay, what was your next column in your truth table? The negation of it. So how do you write a negation? Triangle to hold the knot, and that output is the NAND, right? Technically that's it. Okay, then the next column was what? Or with a Z. Or that, right? This input is XY, this output is X NAND Y. We're going to take that output and Z, and we're going to OR them, so let's make it big Z. Sorry, big OR. So those are 2 inputs. What's the output now? We're going to take X, NAND, Y. We're going to take Z, and we're going to OR them, right? I mean, that's what we got so far. Then the last step, you're going to negate that, and it's X, NAND, Y, NOR Z. Okay. Now, but you're not done. Read the question.
No,
Oh, wait, we didn't read the question for page 3. The truth table said you are a newbie at R&D. Your boss, Sir Charles Babbage, wants you to test output for the following Boolean operation. But now you're a noob in engineering, and your boss, the lady Ada Byron Lovelace, tells you to build the following circuit. Test the circuit by inputting X is 0, Y is 0, and Z is 1. All right, so let's do that. We're going to only run 1 row of the truth table and see if it matches the truth table. That's like a check, right? So, what's X and Y if X is 0 and Y is 0? 0. What's the negation of X and Y? 1. All right, what happens when you take 1 and you OR it with 1? You get 1. And then you negate that, you get 0. Now keep that in your mind. 0, 0, 1, 0, 1, 1, 0. That's got to be in your truth table. We did something wrong. 0, 0, 1, 0, 1, 1, 0. This line is what we tested. Perfect. You can test any row you want, but we tested that 1 row. Okay? So, this test tomorrow should be a piece of cake, right? So this is truth table, there's a circuit that goes with it, and we tested it with 0, 0, 1. You can test it with whatever, because that's what you wanted. That's what we did. And then there's all your binary craziness. Well, we don't do that. All your binary craziness. 4-bit computer, signed numbers, and this was a hex and binary stuff. Amazing. We did everything. All right, so you're done. Okay. All right, we're about done. That's it. That's good for today.
Oh, yes, we're finished.
Yes, we're finished. All right, so you're going to get 100 tomorrow, right? Because this is your last chance to get this down. This is the third test on this kind of stuff. Oh, my goodness. All right, YouTube, we're done. Bye-bye.